Hello, welcome back to the course on audio signal processing for music applications. This week we're talking about the sinusoidal model, and we are considering sinusoids in the frequency domain, in the spectrum. And more particularly, we are considering that a sinusoid is a peak, a spectral peak, and from which we can measure the values of the sinusoid. So this is what we want to go over in this programming lecture from a programming perspective, therefore developing some code that would allow us to measure the values of the sinusoid. And these are the equations we presented in the lecture class to measure the frequency, amplitude, and phase of a sinusoid using parabolic interpolation. So this first equation is the way to compute a parabola on the tip of a peak and obtaining the refined frequency value as this is as a location from 0 to n, which is the FFT size. Then we can obtain the frequency value in hertz by multiplying by the sampling rate and divided by capital N, and then we can plot the location value in the parabola and obtain the tip of it, which will be the interpolated amplitude value. And finally, we can also get the phase value by reading the location of the frequency, maybe using a linear interpolation of that in the phase spectrum, so that we get a refined phase value. Okay, so let's go to text editor. And in here I wrote some code to actually do this detection of a spectral peak. So here I first imported some of the packages that I need, like the NumPy and Matplotlib, the window from SciPy. Then I go to append the directory from which I have some code that I am going to use, specifically the DFT model, so our DFT implementation, and a set of utility functions that I have in the SMS Tools package. Okay, after I have all these packages, I can start like reading a sound file. So I read a sound file that includes a sine wave of 440 Hertz, so I know exactly what frequency I should get. And then I declare some variables that are going to be useful for computing the DFT. So M is our window size, so how many samples of the sine wave I'm going to compute. The N is the FFT size. And T is a threshold that I will be using for the peak detection. Okay, so then I can get the window. I get a Hamming window of size M. Then I read into the file sort of in the middle of the sound file, so I can just get M, capital M samples of the middle of the sound, and then I can compute the spectrum using the DFT-NL. I return the magnitude and phase, and then I'm computing the peak. Okay, so this peak detection, this is a function that is declared in the utility functions. So let's go there. This is the peak detection function that has as input magnitude spectrum and T, which is a threshold. The magnitude spectrum is just the array of values, of amplitude values in decibels, and T is the threshold in decibels that is going to be used to consider the minimum value below which we are not going to consider to have peaks. So the computation is quite simple. We check for three conditions in the whole magnitude spectrum. Well, the whole, we are discarding the initial value 0, and the last value. So within between 1 and the size -1, we are looking for the values that are above a threshold, okay, above T, the values that are higher than the previous and the next values, okay, so that there are local maxima. And then we are considering the peaks as being the values that fulfill the three criteria. They are above a threshold, they are above the next value, and they are above the previous value. And then, well, we add one in order to undo this one that the condition that we had, and it returns the locations, an array of peaks, of the locations of those peaks. So if we can go back to our code, okay, so we call the peak detection, it returns the locations, and then to get the magnitudes of those locations, we just read those values from the magnitude spectrum. To plot that, well, we have these lines for plotting, in which we define first frequency axis, so we're going to be able to see the x-axis in hertz. Then we plot the whole magnitude spectrum, so with the frequency axis and the magnitude spectrum, and we plot the peak locations on top of that. So we plot the locations and the magnitudes, and we're going to plot an x on those locations, okay, without any line. So we just see those locations. So let's run that. We are in this in the workspace of SMS tools, and I have this test.py, so I can just run test. Okay, and this is the spectrum of the sinusoid, and of course it has a main lobe of the Hamming. So let's zoom into that location. So let's just go into just the peak. Okay, and this is the peak of the sinusoid. We can see the cross, and we can see some of the higher samples of the magnitude spectrum. Okay, so in here we can see that the cross is at location 429 hertz, more or less, or 430 hertz. That's clearly quite far from the 440 hertz. Why is that? Well, this is because our size, the FFT size, was 512 samples. And with 512 samples, we have quite a bit of distance between two consecutive samples. In order to compute exactly what is that distance, we can just do the sampling rate, 44,100, divided by the FFT size, which was 512, and 86. This is the distance in hertz between one sample, which is here it says 400 and around 28, and in here is 515 kind of thing. So this is the 86 samples distance between these two. So to improve the resolution, we can now increase the FFT size. So in here the n, let's make it 4 times bigger. For example, let's make it to 2048 samples. So this should give us better frequency resolution. Let's try that. So we save that, and in here, well, let's remember this plot. So we can now, if we run again and we zoom into the tip of the spectrum. Okay, yeah, we can see that there is more samples now, and in fact if we even zoom more, okay, we can see that well, now the tip, the peak, has been computed to be around 430 hertz, okay, and clearly the distance between two consecutive samples has reduced. So in fact it should be 4 times smaller. If we compute that, we can just compute 44,100 divided by 2048. So now it's 21 hertz, the distance. But still is not the frequency we would like to have. It's a little bit far. In fact, this 21 hertz resolution is not ideal. So what we're going to do is to do this parabolic interpolation. So in the util functions file, there is this peak interp function that performs parabolic interpolation on this location that we have found. So from the magnitude spectrum, the phase, and the locations that it found, these local maxima, this function computes the interpolated values. So from the three highest peaks of each local maxima, the actual local maxima and left and right values, it performs the parabolic interpolation to refine the frequency and find the center of the parabola. Then it finds the tip of the parabola, the magnitude of it, and then it uses the location to look into the phase spectrum and perform some linear interpolation, because the phase during this value should be quite flat, and it performs a linear interpolation to find the actual phase value, and it returns these three. Now let's get these three output values. So let's copy them and put them in our little program. So we will obtain these by calling the peak interpolation function. So let's copy that too. Copy, and we put it here. Okay, so this is our peak interpolation function. No need to compute the Pmax. So now it returns the interpolated location, interpolated magnitude, and interpolated phase by calling the peak interp and sending it the magnitude, phase, and location values. So now we can plot the IP log and IP mac, and okay, so let's see if we improve this plot. No, so that we had the peak at 430 hertz. See what we can do with now this interpolation. So let's run again test. Okay, it complains about peak interp because it's part of the package UF, so I have to specify that it comes from there. And let's run it again. Okay, now let's zoom into the tip of it so we can see how it does. Okay, and we can zoom a little bit more. Okay, so here we see the values we had before. So the tip before, it was this tip, so it was like around 430, and now it has found the cross is in between these two locations, so it has moved the tip, because it considers this the tip of the parabola, and now the cross is closer to 440. Still is not at 440. In fact, it's around 439 or so. So we are still 1 hertz kind of difference, but definitely it's much better than what we started with. Okay, so that's basically I wanted to show. So with this code, we can analyze a spectrum of a sound and identify the spectral peak locations that are within that spectrum. Of course, if the sound is more complex than a sine wave, and the threshold is also lower, it will not just find one single peak, it will find many peaks. Okay, let's go back to the slides. And okay, so we have been using the sinusoidal model, and part of it, the concept of peak detection, and using some of the packages of Python, NumPy, SciPy, Matplotlib, and some of the functions available in the SMS Tools package. We have been able to measure the spectral peaks of a sound, and with that we are now ready to go to the next stage, which we'll be talking about in the next programming class, of actually handling more real sounds, and both analyzing and synthesizing these sinusoids. So I hope to see you next class. Bye-bye.